Hey everyone, welcome to your last video for this semester. So this one's going to be real short. We're just talking about uncountable sets. We're not going to do a lot with uncountable sets. You kind of need a lot of background to work with them and stuff like that, but we're going to do some very classic things with them. And yeah, so let me share my screen and then we'll go ahead and get started here. So like in the last video, you saw that the real numbers and this interval 0 to 1 are uncountable. We're going to talk about kind of how you prove something is uncountable here. So a set is uncountable if it's not countable. Okay, it's not super useful. So how do we prove something that really doesn't exist, right? Well, you can do a diagonalization argument, right? Or you can do other things by showing a set is infinite and then showing it doesn't have a bijection to the natural numbers. That would also work. So let's start with this one. So let's start with the interval 0 to 1 is uncountable. So what do we need to do? Well, we're going to do a proof by contradiction. Okay, and this is what I was talking about. We're going to assume there is a bijection, and then we're going to say, hey, this bijection doesn't work. Okay, so assume f from 0 to 1, or sorry, n to 0 to 1, n to 0 to 1 is a bijection. Okay, we can't specify what the bijection is, right? We have to kind of take a general bijection-ish thing and then show that it's not going to work. Okay. So for some x in n, okay, what are we going to say? We're going to say f of x is equal, we'll call it ax. So it's going to map us somewhere, and we don't know where it is, but this ax is in 0 to 1. Okay, so what does this mean? This means that ax has some decimal expansion, right? Because it's in 0 to 1. So it's going to look like point blah, 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 blah. So this means that ax is equal to some point ax1, ax2, ax3, all the way down, right? It has some decimal expansion. So if ax is irrational, so what happens if ax is irrational? Then the decimal expansion is unique, right? Because it can't be reduced or anything like that. So then the decimal expansion is unique, right? You can't reduce it or anything. If it's rational, then it may not be unique, right? Because maybe we can reduce it or something like that. So we'll assume it's not unique. So we're rational. Okay, so we're going to assume the decimal expansions are 0 from some position on. So it's going to go, since we're rational, we're going to assume it's going to be like 0.1, 2, 3, 4, 7, 8, 12, all the way, and then 0, 0, 0, 0, 0, 0, 0, 0, 0. So this means that the function kind of looks like this, where f of 1 is equal to point A11, A12, A13, A14, and so on. F of 2 is going to equal point A21, A22, A23, and so on. I'll do one more. So this is going to be point A31, A32, A33, A34, and so on, right? But this function is creating a list of all the real numbers between 0 and 1, right? So what we're going to do is we're going to choose. We're going to choose some y. Choose some y in the real numbers, okay? Such that y is equal to point, and then we'll do 9 minus a11. Okay, then 9 minus a22, 9 minus a33, and so on. But what did I just do? What did I just do? I just created a new element that's not appearing in my list here, right? Notice that the number I just created will never appear. It won't ever appear. And I'll end with 9 minus a I don't know what I is, but at some point, this number won't ever exist. So I just created a new number in my bijection. So I must not have had a bijection to begin with. So this is my contradiction. Okay, this is just a very not super rigorous proof of how to do this, but this is called Cantor's diagonalization argument. Okay, this is called Cantor's diagonalization argument. Okay, and if we wanted to show the real numbers were uncountable, how would we do it? Well, 0 to 1 is a subset of the real numbers, and this right here is uncountable. And if our subset is uncountable, clearly our larger set is uncountable. So on your homework, you'll actually prove that they have the same cardinality. And by homework, I mean, I'm just going to give you practice problems to work on. You don't actually have to turn them in. So there's this cool thing. It's called the continuum hypothesis, right? The continuum hypothesis is neither true nor false. And it's actually been proven to be independent, right? So meaning that we can't prove it and using our usual like rules of math. Okay, the continuum hypothesis wants to know, is there some infinity between the natural numbers and the real numbers, right? The real numbers are uncountable, the natural numbers are countable. Is there like an infinity that's in between there? Like, can we come up with a set that's in between? No one knows, right? Some people believe it, some people don't. And yeah. Anyway, that's what I wanted to show you, just kind of how you would kind of do this uncountable thing. Do the one practice problem, but really we'll try to stick to those countable problems for our final exam. Maybe as like a bonus question, I may put one that's uncountable. We'll see. Anyway, that's all I have to say, and I'll see everyone later.